For centuries, the greatest minds in history believed that the universe was a grand mechanical masterpiece. This is what we call classical physics, the physics of Isaac Newton and the scientists who followed in his footsteps. To them, the universe was like a magnificent giant clock made of infinite gears and springs. They believed that if you could only measure the position and the speed of every single particle in existence, you could, in theory, predict the entire future of the universe with perfect accuracy. In this classical view, everything is deterministic. There is no room for maybe or perhaps. A ball is either at point A or point B. It travels at a specific speed. It follows a specific path. It was a world of absolute clarity. Imagine a billiard table covered in smooth green felt. When the cue ball strikes another, the resulting movement is a beautiful display of geometry. You can see the angles, you can feel the momentum, and you can calculate exactly where each ball will stop. This is how we have viewed reality for most of human history. We assume that the small things in life are just tinier versions of the big things. We assume that an atom is just a very small billiard ball, and that an electron is just a very small planet. But as we began to develop tools that allowed us to peer into the microscopic heart of matter, we discovered a shocking truth. The billiard table is a lie. To understand why our intuition fails us, we must take a mental journey downward. Close your eyes and imagine you have a magical dial in your hand that allows you to shrink. As you turn the dial, the room around you begins to grow. The dust motes, dancing in the air, become as large as birds. You shrink further, passing through the surface of your own skin, seeing the vast, complex cities of your cells, with their buzzing machinery and flowing rivers of chemistry. But we are not stopping there. We turn the dial further, shrinking past the cells, past the complex strands of DNA, down into the world of individual molecules. At this level, things still feel somewhat familiar. Molecules are like little constructions, balls of atoms held together by invisible sticks of force. But as we turn that dial one more time, shrinking down to the size of a single atom, the lights of common sense begin to flicker and go out. We have reached the threshold. We are standing at the gateway of the subatomic realm. In this realm, the smoothness of the world disappears. Imagine you are looking at a high-definition television screen. From across the room, the image is perfect. A sunset, perhaps, with colors blending seamlessly into one another. But if you walk right up to the glass and press your face against it, you see that the sunset isn't smooth at all. It is made of tiny, square pixels. The smoothness was an illusion created by your distance. The quantum world is the pixelated version of reality. The word quantum itself refers to the idea that at this fundamental level, things come in packets or chunks. You cannot have half a pixel of light or a third of a step of energy. This graininess of the universe is the first great shock to our classical intuition. In our everyday lives, we can move as slowly or as quickly as we like. We can change our speed by the tiniest, most infinitesimal fraction. But in the quantum world, an electron doesn't move smoothly from one place to another. It jumps. It exists here, and then, without ever traveling through the space in between, it exists there. It is as if you were walking up a flight of stairs, and, instead of stepping from one tread to the next, you simply vanished from the bottom step and reappeared on the third. This is the quantum leap, and it marks the end of the mechanical clockwork universe. In this new world, We must learn to speak the language of probability rather than certainty. We must get used to the idea that a particle doesn't have a location in the way we think of it, but rather a tendency to exist in certain places. It is a world where things can be waves and particles at the same time, and where the very act of our looking at them can change what they are doing. It is okay if this feels dizzying. One of the greatest physicists of the 20th century, Richard Feynman, once famously remarked that if you think you understand quantum mechanics, you don't understand quantum mechanics. The goal of our journey tonight is not to force these ideas into the old boxes of your classical common sense. Instead, we are going to build a new set of boxes. We are going to sit by the fire of this mystery and let the warmth of these strange truths wash over us. As we stand here at this gateway, looking out into the shimmering, probabilistic haze of the subatomic world, we realize that the solidity of the chair you are sitting in is actually a miraculous result of billions of tiny, buzzing quantum events. The world is not a machine. It is a symphony. It is a vast, interconnected field of energy that only looks like solid matter because we are looking at it from so far away. With this sense of wonder beginning to take root, let us step through the gateway. Let us leave behind the predictable billiard balls of the past and move toward a mystery that first revealed itself not in a laboratory, but in the simple, warm glow of a heated oven. This transition from the certain to the uncertain, from the smooth to the pixelated, leads us naturally to the first great crisis of modern physics, a problem that the old clockwork laws simply could not solve. That's what we'll gently explore next. The ultraviolet catastrophe, a crisis of classical light. A moment ago, we ended with the idea of the universe losing its smooth, clockwork clarity as we approached the atomic gateway. We felt the first tremors of a reality that is pixelated rather than continuous. To understand why this shift was so necessary, we must travel back to the late 19th century, into the dimly lit laboratories where scientists were struggling with a problem that seemed humble at first, but would eventually threaten to pull apart the very fabric of physics. This was the era of the black body, and the crisis it created is what we now call the ultraviolet catastrophe. Let us imagine together a simple object, a hollow metal box with a tiny pin-sized hole poked into one side. In the world of physics, we call this a black body. It is an idealized object that absorbs all the light and radiation that falls upon it, reflecting nothing. Because it reflects nothing, any light that comes out of that tiny hole isn't a reflection. It is the pure signature of the object's internal heat. You have seen this in your own life, perhaps while watching a campfire or staring at the coils of a toaster. As an object gets hotter, it begins to glow. It starts with a deep, barely visible red, then moves to a bright orange, a yellow, and eventually, if it gets hot enough, a brilliant, bluish white. Classical physics, the physics of the great Isaac Newton and James Clerk Maxwell, tried to explain this glow. They used a principle called the equipartition of energy. Imagine you have a large room filled with different types of musical instruments, violins, cellos, and massive bass drums. The equipartition theorem suggested that if you heated the room with energy, every possible way that room could vibrate should get an equal share of that energy. In our metal box, the light waves are the vibrations. There are long, slow waves, which we see as red light, and there are short, rapid waves, which we see as blue or violet light. Now, picture the space inside that box. You can fit a few long, lazy waves from one side to the other quite easily. But as the waves get shorter and shorter, moving into the blue and ultraviolet part of the spectrum, you can fit more and more of them into the same space. In fact, mathematically, there is no limit to how many short waves you can cram into the box. Classical logic dictated that since every possible wave gets an equal share of energy, and there are an infinite number of short ultraviolet waves possible, the box should radiate an infinite amount of energy in the ultraviolet range. Think about the implications of this for a moment. If this classical law were true, every time you heated a piece of metal, or even turned on a light bulb, it wouldn't just glow with warmth. It would instantly release a blinding, infinite blast of ultraviolet rays, X-rays, and gamma rays. A simple kitchen oven would become a lethal source of radiation the moment it reached a certain temperature. This was the catastrophe. It wasn't just a small error in a calculation. It was a total breakdown of reality. The math said the oven should kill you with invisible light, but our eyes and our skin told us that it simply glowed a gentle, comforting red. You might picture this discrepancy as a graph in your mind, a map of how much light is released at different colors. According to the classical theory, as the colors move from red to violet, the line on the graph should soar upward like a rocket, higher and higher, never coming down, heading toward that infinite ultraviolet peak. But when scientists actually measured the light in their labs, they saw something entirely different. The line would start low at the red end, rise to a pleasant peak in the middle, and then instead of soaring, it would gracefully curve back down to zero as it reached the ultraviolet. Nature was refusing to follow the rules of fairness. For some reason, the high-frequency, short wavelength light was being suppressed. It was as if the universe were saying that while it's easy to create a low-energy red wave, it becomes expensive or difficult to create the high-energy ultraviolet ones. This was the wall that the greatest scientists of the time hit. They had a theory that worked perfectly for the large world for planets and steam engines, but it failed utterly to explain the light coming from a heated box. The crisis of the ultraviolet catastrophe was a signal that something was deeply, fundamentally wrong with our understanding of how energy and matter interact. It suggested that we could no longer think of energy as a continuous fluid that can be divided into smaller and smaller pieces forever. If energy were like water, you could always take half a drop and then half of that, and so on. But the experimental data from the blackbody suggested that energy doesn't work that way. It suggested that there is a limit, a minimum price that must be paid to create a wave of light. Imagine you are at a carnival, and there is a game where you have to throw a ball to win a prize. In the classical world, the prizes of light are free. You can have as many as you want of any color. But in the real world of the blackbody, the violet prizes are very expensive. Unless you have a massive amount of heat, you simply can't afford to create a violet wave. This is why a warm oven only glows red. It has enough energy to buy the cheap red waves, but not enough to pay the high price for the ultraviolet ones. This realization was the first time humanity glimpsed the staircase of reality. It was a moment of profound confusion and excitement. The scientists of the time were like explorers who had reached the edge of a map they thought was complete, only to find a vast, mist-covered ocean stretching out before them. They realized that the equipartition of energy, the idea that energy is shared equally among all frequencies, was a myth. The universe was more selective. It was more disciplined. It was quantized. This transition from the soaring, infinite failure of classical physics to the measured, curving reality of the laboratory forced a total rethink of the natural world. It set the stage for a quiet, modest man to step forward with a solution that he himself found almost impossible to believe. He would take the broken pieces of this catastrophe and use them to build a new foundation. Before we rest here, let me whisper where we're headed next, not to rush, but to plant a seed of what comes when we finally accept that energy has a minimum size. Let's set that idea of the expensive ultraviolet light down now, fully formed, and let our attention drift toward the man who first calculated the cost of those energy packets. The birth of the quantum, Planck's constant and energy packets. A moment ago, we ended with the idea of expensive ultraviolet light and the realization that the old laws of the universe were failing to explain the simple glow of a heated object. It is right here, in this moment of scientific crisis, that we meet Max Planck. He was a man of deep tradition, a physicist who loved the elegant, smooth equations of the past. He didn't set out to start a revolution. He simply wanted to fix the math. But in his attempt to mend the old world, he accidentally discovered the foundation of a new one. Let us pick up that thread right where we left it, with Planck sitting at his desk in Berlin in the year 1900, staring at the data that refused to behave. Planck realized that to make the math match the reality of the glowing oven, he had to make a desperate assumption. He had to assume that energy was not like a continuous, flowing river that could be divided into any amount, no matter how small. Instead, he proposed that energy is delivered in tiny, discrete packets or bundles. He called these bundles quanta. To understand the weight of this, imagine you are standing at the base of a long, smooth ramp that leads to a high balcony. In the classical world of the past, you could walk up that ramp and stop at any height you desired. You could stand precisely 2.5 inches off the ground, or 2.555 inches. There were no limits to your position because the ramp was continuous. But Planck's new quantum world is not a ramp, it is a staircase. As you move up a staircase, you can stand on the first step, or the second, or the third. But there is no such thing as standing between the steps. You are either on one level of energy, or you are on another. The space in between the in-between energies that the old laws predicted simply does not exist in the quantum realm. This was a radical departure from everything humans had observed for thousands of years. It suggested that nature has a minimum grain, a smallest possible unit that cannot be broken down any further. To give this idea a mathematical backbone, Planck introduced a number that would become one of the most important constants in all of science, Planck's constant. In your mind's eye, I want you to imagine this constant as the size of the steps on that cosmic staircase. It is an unimaginably tiny number, far smaller than a grain of sand or a speck of dust. But it is not zero. Because it is not zero, the universe has a texture. If you were to pour a glass of water, it looks like a smooth, silver stream. But Planck realized that if you could look closely enough, closer than any human eye ever could, you would see that the water of energy is actually made of individual drops. The relationship he discovered was deceptively simple when spoken aloud. The energy of a single packet is equal to this tiny Planck's constant, multiplied by the frequency of the radiation. Let's pause to let that settle in your mind. Frequency refers to how fast a wave is vibrating, how many times it wiggles up and down in a single second. Low-frequency light, like the deep red glow of a dying ember, wiggles slowly. High-frequency light, like the bright violet at the edge of a rainbow, wiggles very, very fast. Because energy is linked to frequency through this constant, Planck's discovery explained the ultraviolet catastrophe perfectly. Remember the expensive light we discussed? Since violet light has a very high frequency, the size of its energy packets, its marbles, if you will, is very large. To create even a single packet of violet light, an atom needs a significant amount of energy. If an oven is only moderately hot, it simply doesn't have enough energy to buy those large violet packets. It can only afford the smaller, cheaper red packets. This is why the line on the graph doesn't soar to infinity. It drops off because the price of high-frequency light becomes too high for the system to pay. Planck himself was deeply uneasy with this discovery. He called it an act of despair. He thought he had found a mathematical trick, a way to make the equations work on paper, but he didn't truly believe that nature actually functioned this way. He assumed that, eventually, someone would find a way to return to the smooth, continuous ramp of classical physics. But the universe does not care for our comforts. Planck had pulled a single thread, and the entire tapestry of classical reality was beginning to unravel. Consider the graininess of the world for a moment. We often think of our lives as a smooth progression of time and movement. But Planck's constant tells us that at the very bottom of everything, there is a limit to how smooth things can be. It is the pixel size of reality. Just as a digital photograph is made of tiny dots of color that only look like a face when you step back, the solid world you touch is made of these discrete quantum steps. This constant is the bridge between the world we see and the world as it truly is. It dictates the size of atoms, the stability of matter, and the way light interacts with our very eyes. Every time you see the green of a leaf or the blue of the sky, you are witnessing Planck's constant in action. The leaf absorbs specific packets of light energy and reflects others. It isn't taking in a random smooth smear of energy. It is interacting with the universe one step at a time. This transition from a world of any amount to a world of specific amounts is the birth of the quantum. It is the moment we realize that nature is not a fluid, but a collection of beautifully organized parts. As we let this idea of the staircase of energy rest quietly in our minds, we begin to see the profound ripple effect it had on the scientific community. Planck had defined the packets, but he still thought of light primarily as a wave that just happened to be delivered in chunks. It would take a different kind of mind, one that was willing to be even more radical to suggest that these packets weren't just a mathematical convenience, but physical objects in their own right. This brings us to a young patent clerk in Switzerland who was about to take Planck's marbles and use them to explain how light can literally knock pieces of metal apart. So what does this actually mean for how light behaves when it hits a surface? That's what we'll gently explore next, as we turn our attention toward the surprising reality of the photoelectric effect. The photoelectric effect. Light as a stream of particles. So what does this actually mean for how light behaves when it hits a surface? That is what we shall gently explore now, as we turn our attention toward the surprising and beautiful reality of the photoelectric effect. To understand this, I want you to first imagine a warm, sunny afternoon. You are standing outside, and you feel the sun's rays washing over your skin like a gentle, continuous stream of warm water. For almost a century, this was exactly how the greatest scientific minds thought of light as a smooth, undulating wave that rippled through the fabric of space much like a swell moving across the surface of a deep blue ocean. It was a comforting, elegant idea. But hidden within that sunlight is a secret that waves alone cannot explain. A secret that would eventually earn Albert Einstein his Nobel Prize and change our understanding of reality forever. Imagine a thin plate of polished metal, perhaps zinc or potassium, sitting in a dark room. This metal is made of atoms, and those atoms have electrons, tiny, negatively charged particles clinging to them, like small, restless birds perched on the branches of a tree. These electrons are held in place by an invisible force, a sort of energy glue that keeps them bound to the metal. If you want to knock one of those electrons off the plate, you have to hit it with enough energy to break that bond. In the late 1800s, scientists began to shine different colors of light on these metal plates to see what would happen. According to the old, classical way of thinking, light was a wave. If you wanted to knock an electron loose, the most important thing should have been the brightness, or the intensity, of the light. Think of a wave at the beach. A tiny, 6-inch ripple won't move a heavy log, but a massive, 10-foot wall of water will easily toss it aside. The scientists expected that if they shone a very bright, very intense red light on the metal, the sheer volume of the wave would eventually give the electrons enough energy to go flying off. But nature had a surprise in store. No matter how bright they made the red light, even if it was a blinding, searing crimson glare, not a single electron would budge. It was as if the electrons were completely indifferent to the intensity of the light. Yet, the moment they turned on a very dim, very faint blue or violet light, electrons began to jump off the metal instantly. It didn't make sense. Why would a massive wave of red light fail while a tiny, weak ripple of blue light succeeded? This is where Albert Einstein stepped in, looking at the packets of energy that Max Planck had described just a few years earlier. Einstein realized that we had to stop thinking of light as just a wave and start thinking of it as a stream of individual particles. He called these particles of light photons. Each photon, he suggested, carries a specific amount of energy that depends entirely on its color, or, more accurately, its frequency. To picture this in your mind, let's imagine the electrons on that metal plate are like heavy bowling pins standing at the end of a long lane. If you want to knock a pin over, you have to hit it with something that has enough individual punch to move it. Now, imagine that red light is like a stream of millions of ping-pong balls. Because red light has a low frequency, each individual red photon is light and weak. You can throw 1,000,000 ping-pong balls at a bowling pin, but no matter how many you throw or how fast you throw them, each individual impact is too small to knock the pin over. They simply bounce off, leaving the pin standing exactly where it was. This is why a bright red light does nothing to the metal. It's just a vast number of weak ping-pong ball photons hitting the electrons. But blue or violet light is different. Because blue light has a high frequency, each individual blue photon is like a heavy, solid bowling ball. Even if you only throw one single bowling ball, it has enough concentrated energy in that one packet to strike the pin and knock it flying. It doesn't matter if the light is dim, which just means there are fewer bowling balls, because every single ball that does hit a pin has the strength to get the job done. Einstein described this mathematically in a way that we can express simply in words. The energy of a single photon is equal to Planck's constant multiplied by the frequency of the light. If that energy is greater than the work function, which is just a fancy way of saying the cost of breaking an electron free from the metal, then the electron is ejected. If the photon's energy is lower than that cost, the electron stays put. Any extra energy the photon has left over after breaking the electron free simply becomes the speed or the kinetic energy of the electron as it zooms away. This was a revolutionary realization. It proved that light has a dual nature. It travels through space like a wave, but it interacts with matter like a hail of tiny bullets. This wave-particle duality is the cornerstone of the quantum world. It tells us that the universe is not just one thing or another. It is both. It is a world where the very nature of an object changes depending on how it interacts with its surroundings. As you lie there, let the image of these light bullets, these photons, settle into your mind. Think of the trillions of photons from a nearby lamp or the distant stars, each one a tiny, discrete packet of energy, dancing across the room and striking the surfaces around you. This discovery didn't just explain a lab experiment. It gave us the tools to build the modern world. Every time you walk through an automatic door at a grocery store, a beam of light is striking a sensor, using the photoelectric effect to create a tiny current of electrons that tells the door to open. Your digital camera uses these same photons to knock electrons loose and create the pixels of a photograph. But as profound as this was, it raised an even deeper, more unsettling question. If light, which we were sure was a wave, can act like a particle, what does that mean for the things we were sure were particles? What does it mean for the very atoms that make up your body? This leads us to one of the most famous and baffling experiments in the history of science, an experiment that challenges our very definition of what it means for something to exist in a specific place. Before we move on, let the warmth of this photon rain comfort you. The universe is more complex and more wondrous than we ever dared to imagine, and we are just beginning to see the patterns in the chaos. We have seen that light has a split personality, acting as both a wave and a particle, a concept that will soon lead us to a famous and baffling experiment where we watch the very fabric of reality shift before our eyes. Let's set that idea of the light bullet down now and let our attention drift toward the mystery of the double slit. The mystery of the double slit, the duality of reality. Before we move on, let the warmth of this photon rain comfort you. The universe is more complex and more wondrous than we ever dared to imagine, and we are just beginning to see the patterns in the chaos. We have seen that light has a split personality, acting as both a wave and a particle, a concept that will soon lead us to a famous and baffling experiment where we watch the very fabric of reality shift before our eyes. Let's set that idea of the light bullet down now and let our attention drift toward the mystery of the double slit. To truly feel the strangeness of the quantum world, we must picture this experiment in our minds, for it is here that the nature of reality reveals its most guarded secrets. Imagine you are standing in a vast, silent laboratory, draped in soft shadows. In the center of the room, there is a device, let's call it an electron cannon. It is designed to fire tiny particles of matter, one at a time, with perfect precision. A few feet in front of this cannon, imagine a tall, solid barrier. In the middle of this barrier, two narrow vertical slits have been cut, side by side, like two thin, glowing lines of light in the darkness. Farther back, behind this barrier, stands a large detection screen, a sensitive surface that records exactly where each particle lands, leaving a tiny, glowing dot of light to mark its arrival. Let us start with what our common sense tells us should happen. Imagine we are firing small, solid marbles at those two slits. Some marbles will hit the solid part of the barrier and bounce back, but some will pass through the left slit and some will pass through the right slit. On the back wall, we would expect to see two distinct vertical bands of marks, one band directly behind the left opening and one band directly behind the right. This is the world of particles. It is predictable, logical, and clear. Each marble is a single thing that takes a single path through one hole. But now, let us replace the marbles with a wave, like a ripple on the surface of a still pond. Imagine a long, straight wave front, traveling toward our barrier. When the wave hits the two slits, it doesn't just stop. Instead, two new, circular ripples emerge from the other side of the slits, spreading out and overlapping with one another. This is where the magic of interference happens. Picture the surface of the water, where the peak of one ripple meets the peak of the other. They combine to create a taller, more powerful wave. But where the peak of one ripple meets the valley of another, they cancel each other out, leaving the water perfectly flat and still. When this overlapping wave finally reaches the back wall, it doesn't leave two bands. Instead, it creates what we call an interference pattern. Imagine a row of many stripes on the screen. In the center, where the waves from both slits reinforced each other most strongly, there is a bright, intense band. Moving outward to the left and right, you see a dark space where the waves canceled out, then another bright stripe, then another dark space, and so on. This stripy pattern is the unmistakable signature of a wave. Now, we come to the great quantum mystery. What happens when we fire electrons, which we have always thought of as solid little marbles of matter, at these two slits? If we fire a whole stream of them at once, they create the striped interference pattern. You might think, well, maybe the electrons are just bumping into each other as they fly through, like a crowd of people pushing through two doors. So, to be sure, we slow the experiment down. We fire the electrons, one by one by one. Imagine it now. The first electron is fired. It passes through the barrier and hits the back screen with a single, sharp click, leaving a single dot. Then another, then another. At first, the dots seem scattered and random. But as we wait, and as thousands of individual electrons are fired over several hours, a pattern begins to emerge from the silence. The dots are not forming two simple lines. They are building up that same striped interference pattern. Think about what this means. Each individual electron, traveling all by itself through the darkness, must have somehow interfered with itself. It's as if each electron didn't choose the left slit or the right slit. Instead, it traveled as a wave of possibility that passed through both slits simultaneously. It existed in two places at once, overlapped with itself on the other side, and then only when it hit the back screen did it choose a single point to land. But the mystery deepens even further. Suppose we are bothered by this. We want to know which slit the electron really goes through. So, we place a tiny, sophisticated detector next to the slits to watch the electrons as they pass. We tell ourselves we will just peek at them to see which path they take. The moment we turn that detector on, the universe changes its behavior. As soon as we know which slit the electron goes through, as soon as we observe it, the interference pattern on the back wall vanishes. The electrons stop acting like waves and go back to acting like boring, solid marbles. They form two simple lines, just like the marbles did. The very act of looking at the electron, the simple act of gathering information, collapses its wave of possibility into a single, definite reality. It is as if the universe is a shy performer that only dances in waves when no one is watching, but stands perfectly still and solid the moment it feels an eye upon it. This suggests that at their core, all things electrons, atoms, and perhaps even you and I exist as a shimmering cloud of maybe until we interact with them. Reality is not a fixed, solid stage. It is a collaborative process between the observer and the observed. This duality, the ability of a single object to be both a spread-out wave and a localized particle, is the central paradox of quantum mechanics. It tells us that our common sense is just a thin crust over a much deeper, more fluid truth. We are living in a world where the act of measurement is a creative act, where the paths of the universe are not set in stone until we walk them. As you let this image of the striped screen and the watchful detector settle into your mind, you might begin to feel a sense of profound connection. If an electron can be in two places at once, and if it only settles down when we look at it, then what does that say about the rest of matter? This realization that matter itself has a hidden rhythm, a silent frequency that defines its structure, was taken even further by a young prince named Louis de Broglie. He looked at these electron waves and realized that they weren't just a strange fluke of the laboratory. They were the very music that holds the atom together. So, how does this wave-particle nature apply to the very atoms that make up your body? That is what we'll gently explore next, as we listen for the hidden melody of the universe in the music of matter. The de Broglie hypothesis, the music of matter. So, how does this wave-particle nature apply to the very atoms that make up your body? That is what we'll gently explore next, as we listen for the hidden melody of the universe in the music of matter. Imagine, for a moment, that the universe has a deep, underlying sense of symmetry. If light, which for centuries was thought to be a pure, ephemeral wave, could reveal itself as a stream of particles, then why should the reverse not be true? This was the radical question posed by a young French aristocrat named Louis de Broglie in the mid-1920s. He looked at the solid, tangible world of matter and dared to suggest that it, too, was composed of waves. To understand this, let us settle into the idea of nature's balance. In his doctoral thesis, which was so revolutionary that his professors weren't sure whether to grant him a degree, until Albert Einstein himself vouched for the idea, de Broglie proposed that every moving object has a wavelength associated with it. This isn't just a metaphor, it is a fundamental property of existence. He stated that the wavelength of any object is equal to that tiny number we've discussed, Planck's constant divided by the object's momentum. Now, remember that momentum is simply the mass of an object multiplied by its velocity. Think about what this means for the objects in your room. Imagine a baseball flying through the air. The baseball has a significant mass, and when you multiply that mass by its speed, you get a large momentum. When you divide the tiny, tiny Planck's constant by that large momentum, the resulting wavelength is so incredibly small, far smaller than the width of a single atom, that it is impossible to detect. The baseball's wavy nature is hidden by its bulk. From our perspective, it remains a solid, predictable sphere. But now, let your mind shrink back down to the scale of an electron. An electron has a mass that is almost unimaginably small. Because its mass is so tiny, its momentum is also tiny. When we divide Planck's constant by this very small number, the wavelength becomes relatively large. At the scale of the atom, the wave nature of the electron isn't just a subtle detail, it is the headline of the story. To picture how this wave nature defines the atom, I want you to imagine a guitar string. When you pluck a string that is anchored at both ends, it vibrates. But it doesn't vibrate in just any random way. It forms what we call standing waves. These are patterns where the string seems to stay in place, forming 1, 2, or 3 distinct loops or humps of vibration. You can have a wave with 1 hump, or 2, or 3, but you can never have a wave with 2.5 humps. The wave must fit perfectly between the 2 fixed points of the string. If it doesn't fit, the vibrations interfere with one another and quickly die out. This is why a guitar string produces a specific, clear note rather than a messy blur of noise. Now, take that vibrating string in your mind and gently bend it into a circle so the 2 ends meet and fuse together. This is the image de Broglie used to explain the structure of the atom. Imagine the electron not as a little planet orbiting a nucleus, but as a circular wave of existence wrapped around that nucleus. For the electron to exist in a stable state, its wave must fit perfectly around the circumference of its orbit. The end of the wave must meet the beginning of the wave in a seamless, perfect harmony. If the orbit is just the right size, the wave reinforces itself, creating a beautiful, steady, standing wave of probability. If the orbit is the wrong size, if the wave doesn't meet itself perfectly, the peak of the wave will eventually meet a valley of the wave as it circles around, and the electron's presence will cancel itself out. This is a profound revelation. It explains why electrons are only found at specific energy levels or distances from the nucleus. They aren't just choosing those spots at random. They are the only spots where the music of the electron's wave can exist without destroying itself. The atom is not a mechanical solar system. It is more like a musical instrument, and the electrons are the notes that it is allowed to play. Let this image of a vibrating circle settle into your mind. Picture the nucleus at the center, a tiny, dense point of warmth, and around it, these shimmering, translucent rings of wave energy. These are not flat, two-dimensional circles like a drawing on paper, but three-dimensional vibrations that fill the space around the nucleus. When an electron jumps from one energy level to another, it is like a musical instrument shifting from one overtone to the next. The quantum leap we discussed earlier is simply the wave shifting its shape to a new pattern that fits a different-sized orbit. This matter-wave hypothesis changes the way we think about ourselves. If every particle has a wavelength, then every atom in your body, every molecule in the air you breathe, and every star in the sky has a hidden frequency. We are, quite literally, composed of harmony and interference. The reason you feel solid and the reason you don't feel yourself waving through the world is simply a matter of scale. Your mass is so large that your wavelength is silenced by the sheer volume of your existence. But at the foundation of your being, in the silent depths of your atoms, the music is playing. This realization that particles are waves was the key that unlocked the true shape of the atom. It moved us away from the idea of hard little balls and toward the idea of orbitals. But if the electron is a wave, how do we describe where it is? How can a wave have a location? This leads us to a shift in our journey, moving from the clear lines of orbits to the soft, hazy clouds of probability. We have seen that matter has a rhythm, a vibration that dictates where it can and cannot be. Now, let us look closer at these vibrations to see how they form the clouds that make up everything we touch. A moment ago, we ended with the idea of the electron as a circular standing wave, a note in the symphony of the atom. Let's pick up that thread and see how these waves of matter don't just stay in neat circles, but expand into three-dimensional shapes of maybe. This takes us from the fixed, predictable orbits of the old models to the complex, shimmering electron clouds that represent our modern understanding of atomic structure. That is what we'll gently explore next, as we look at how these quantum numbers act as the coordinates for reality's most fundamental map. Atomic structure, from fixed orbits to clouds of probability. A moment ago, we ended with the idea of the electron as a circular standing wave, a note in the symphony of the atom. Let's pick up that thread and see how these waves of matter don't just stay in neat circles, but expand into three-dimensional shapes of maybe. This takes us from the fixed, predictable orbits of the old models to the complex, shimmering electron clouds that represent our modern understanding of atomic structure. That is what we'll gently explore next, as we look at how these quantum numbers act as the coordinates for reality's most fundamental map. For a long time, we were taught to picture the atom like a tiny solar system. In your mind's eye, you might see a dense cluster of protons and neutrons at the center, to the nucleus with tiny moon-like electrons zipping around it in perfect, flat circles. This was the Bohr model, and while it was a beautiful and necessary step in our understanding, we now know it is only a shadow of the truth. In the quantum world, an electron does not travel along a track like a train. It does not have a flight path that we can trace with a pencil. Instead, the electron is a presence that fills a volume of space all at once. To help you visualize this, imagine a fast-spinning ceiling fan in a darkened room. When the fan is off, you can clearly see the three distinct blades. You know exactly where they are. But when you flip the switch and the blades reach a high speed, they disappear into a translucent gray blur. If you were to throw a small foam ball toward the fan, you wouldn't know which specific blade it might hit, but you know with absolute certainty that it will hit a blade somewhere within that circular area. The electron is like that blur. It isn't moving through the cloud so much as it is the cloud. We call these regions of existence orbitals, and they are the heart of how matter is built. An orbital is not a physical container, but a mathematical map of probability. If you were to take 1 trillion snapshots of an atom and mark the location of the electron with a tiny dot each time, you would eventually see a shape emerge. In some places, the dots would be thick and dense. This is where the electron is most likely to be found. In other places, the dots would be thin and scattered, showing a lower probability. The boundary of the orbital is simply the line where we have a 95% chance of finding that electron. To organize this world of clouds, nature uses 4 specific quantum numbers, which you can think of as the cosmic zip code for an electron. These numbers define the address, the shape, and the behavior of every electron in existence, and they ensure that no 2 electrons are ever exactly the same. The first of these is the principal quantum number. In your mind, imagine the nucleus of the atom as the very center of a large set of nested spheres, like a set of Russian dolls. The principal quantum number tells us which doll or energy level we are in. A low number means the electron is close to the nucleus, held tightly in a small, high-energy embrace. As the number increases, the electron moves into larger, more distant shells, with more room to move and more energy to carry. The second quantum number defines the shape of the orbital. Nature is a diverse architect, and it does not limit itself to simple spheres. The simplest shape, which we call the S orbital, is indeed a sphere. Picture a soft, glowing marble of light surrounding the nucleus. It is perfectly symmetrical, the same from every angle. But as we move to different energy states, the shapes become more complex. Imagine the p orbital. Instead of a sphere, picture two soft balloons tied together at their necks, with the knot sitting right at the nucleus. These teardrop shapes point out into space along an axis. There might be one pair of balloons pointing up and down, another pair pointing left and right, and a third pair pointing toward you and away from you. These are the three dimensions of our world, reflected in the very structure of the atom. The third quantum number, the magnetic number, simply tells us which direction those balloons are pointing. It describes how the orbital is oriented in the space around the nucleus. And finally, there is the fourth number, which we call spin. Although we call it spin, the electron isn't literally rotating like a top. Instead, it is an internal property, a kind of magnetic orientation that can only be up or down. Every orbital, every sphere or pair of balloons can hold exactly 2 electrons, but only if they have opposite spins, like 2 puzzle pieces that only fit together when one is flipped over. As you picture these shapes, the spheres, the dumbbells, and even more complex cloverleaf patterns that we call D and F orbitals, try to see the atom not as a solid thing, but as a vibrating, three-dimensional geometry. It is a structure made of waves that have settled into stable patterns. The electrons fill these shapes starting from the inside out, always seeking the lowest energy state, like water filling a vessel from the bottom up. This arrangement, this electron configuration, is what gives every element its personality. It is why oxygen behaves like oxygen, and why gold shines like gold. The chemistry of our entire world, the way medicines heal and the way fire burns, is determined by the specific shapes of these probability clouds and how they overlap with one another. This shift from where it is to where it might be is a profound one. It requires us to give up the comfort of seeing the world as a collection of tiny, solid bits. Instead, we must see it as a collection of potentials. The electron is a cloud because it is a wave that is spread out, and it only becomes a point when we interact with it in a very specific way. This leads us to a startling realization. If the electron is a fuzzy cloud of probability, then there is a limit to how much we can ever truly know about it at any one time. Nature seems to have a built-in haze that prevents us from seeing everything with perfect clarity. This is not a failure of our technology, but a fundamental rule of the universe itself. As we let these shimmering shapes of the S and P orbitals drift in our minds, we begin to wonder, if the electron is so spread out, how can we ever say where it is going? This transition from the clear, solid shapes of the atom to the inherent fuzziness of reality brings us to the most famous limit in physics. We have seen the where, but now we must confront the how much. This brings us to a fundamental limit of what we can ever truly know, as we move from the structure of the atom to the jittery, uncertain world of Heisenberg. The Heisenberg uncertainty principle, the limits of measurement. We have seen the where, but now we must confront the how much. This brings us to a fundamental limit of what we can ever truly know as we move from the structure of the atom to the jittery, uncertain world of Werner Heisenberg. A moment ago, we explored the three-dimensional geometry of orbitals, those shimmering clouds of probability that define where an electron might be found. But as we look closer at those clouds, a startling question arises. If the electron is spread out like a haze, how can we ever say exactly where it is going, or how fast it is moving? This is not merely a question of better technology or sharper microscopes. It is a question that strikes at the very heart of how the universe is constructed. In the year 1927, Werner Heisenberg gave us one of the most profound and perhaps most unsettling rules of the natural world, the uncertainty principle. At its simplest, The principle states that there is a fundamental trade-off in nature. The more precisely you try to measure the position of a particle, the less precisely you can know its momentum, which is its mass times its velocity. Conversely, if you focus all your efforts on determining exactly how fast a particle is moving and in what direction, you will lose all ability to say exactly where it is. It is as if the universe has a knowledge budget, and if you spend all your coins on one piece of information, you are left bankrupt for the other. To understand why this happens, let us imagine a simple, relatable scene in our minds. Imagine you are in a vast, pitch-black room, and somewhere in that darkness, there is a single helium-filled balloon drifting silently. You want to find it, but because the room is dark, you cannot see it. To find its position, you must interact with it. So, you reach out your hand and sweep it through the air. Eventually, your fingers brush against the soft surface of the balloon. In that instant, you know exactly where the balloon is. It is right there, touching your fingertips. But think about what happened the moment you touched it. To know its position, you had to physically contact it. That very touch, however gentle, gave the balloon a nudge. It pushed it in a new direction and changed its speed. By the time your brain processes the information that the balloon is at point A, the balloon has already been bumped toward point B at a new, unknown velocity. In the world of the very small, this nudge is unavoidable. To see an electron, we must bounce at least one photon of light off it. But an electron is so light and so delicate that even a single photon hits it like a bowling ball hitting a pane of glass. The very act of measurement, the act of seeing, unavoidably alters the thing we are trying to observe. You might also picture this through the lens of photography. Imagine you are trying to take a picture of a race car zooming past you at 200 miles per hour. If you use a very fast shutter speed, say 1/8,000th of a second, you will capture a perfectly crisp, clear image of the car. You can see every detail of the tires and the driver's helmet. You know exactly where the car was at that specific moment. But because the image is frozen, you have no idea how fast the car was going just by looking at the photo. It could be parked there, for all the image tells you. Now, imagine you take another photo with a very slow shutter speed, say a full second. The car now appears as a long, colorful blur stretching across the frame. From the length of that blur, you can calculate the car's speed and direction quite accurately. But because it is a blur, you can no longer say exactly where the car was during that second. It was everywhere within that streak of light. Heisenberg's insight was that this isn't just a limitation of our cameras or our touch. It is a property of the particles themselves. Mathematically, Heisenberg described this by saying that the uncertainty in an object's position, multiplied by the uncertainty in its momentum, must always be greater than or equal to a specific in fundamental value. That value is equal to Planck's constant divided by 4 times the number pi. Let us pause and consider the weight of that statement, because Planck's constant is a real, non-zero number. The result of that multiplication can never be zero. In a classical Newtonian world, that constant was assumed to be zero, meaning you could know everything perfectly. But in our quantum world, the math demands a minimum level of fuzziness. If you make the uncertainty in position very, very small, approaching zero, the uncertainty in momentum must become infinitely large to keep the product above that minimum threshold. The universe simply does not allow a particle to have a definite position and a definite momentum at the same time. It is as if the particle itself hasn't decided where it is or how fast it is going until we force the issue. This realization destroyed the dream of the clockwork universe. It told us that we could never, even in theory, know the current state of the universe well enough to predict its future with absolute certainty. At the very foundation of matter, there is a jitter, a restless uncertainty that can never be smoothed away. This is why the electrons in an atom don't just sit still in the nucleus. If an electron were to settle down perfectly in the center of the atom, we would know its position exactly. But the uncertainty principle says that if we know its position that well, its momentum must become wild and enormous. The electron would jitter so violently that it would fly away from the center. The fuzziness of the electron clouds we discussed is what keeps the atom from collapsing. The uncertainty is the very thing that gives the universe its structure. As we let this idea of the cosmic haze settle in our minds, we realize that we need a new way to describe these particles. If we cannot track them like little balls with positions and speeds, how do we track them at all? The answer lies in the mathematical map we touched on briefly before the wave function. This function doesn't try to cheat the uncertainty principle. Instead, it embraces it, providing us with a shimmering sea of possibilities rather than a single, lonely path. Nature seems to have a built-in haze that prevents us from seeing everything with perfect clarity. This is not a failure of our technology, but a fundamental rule of the universe itself. We have seen the how much, the limit of our knowledge. Now, let us look at the tool we use to navigate this hazy reality. This transition from the limits of what we can know to the way we calculate the maybe of the universe brings us to the most powerful equation in quantum mechanics. We move now from the jittery limits of Heisenberg to the flowing, mathematical map that guides every particle through the dark. That is what we'll gently explore next, as we dive into the sea of the wave function. The wave function, navigating the sea of possibility. Nature seems to have a built-in haze that prevents us from seeing everything with perfect clarity. This is not a failure of our technology, but a fundamental rule of the universe itself. We have seen the how much, the limit of our knowledge. Now, let us look at the tool we use to navigate this hazy reality. This transition from the limits of what we can know to the way we calculate the maybe of the universe brings us to the most powerful equation in quantum mechanics. We move now from the jittery limits of Heisenberg to the flowing, mathematical map that guides every particle through the dark. That is what we'll gently explore next as we dive into the sea of the wave function. Imagine, if you will, that the universe is not made of solid objects, but of a vast, invisible ocean of potential. In the old world of classical physics, if we wanted to know where a ball would be in 5 seconds, we would draw a single, sharp line, a trajectory showing its path from point A to point B. But in the quantum world, we must replace that sharp line with something much more fluid and elegant. We call this the wave function. It is often represented by the Greek letter psi, which looks a bit like a 3-pronged pitchfork, but for our journey, let us simply call it the shimmering map. This map does not tell us where a particle is. Instead, it tells us where the particle could be. Picture a long, translucent silk ribbon floating in a gentle breeze. The ribbon ripples up and down as it moves through the air. Some parts of the ribbon are high, some are low, and some are fluttering near the middle. In the language of the quantum, the height of that ribbon at any given point represents the amplitude of the wave function. Now, imagine that this ribbon is stretched across the floor of a room. If the ribbon is very high and peaked in the center of the room, it means there is a very high probability that the particle is right there. If the ribbon is flat and touching the floor near the corners, the probability of finding the particle there is nearly zero. But there is a specific, beautiful rule that governs this map, discovered by the German physicist Max Born. He realized that the wave function itself is not the probability. To find the actual physical likelihood of finding a particle, you must take the value of the wave function at a specific point and square it, multiply it by itself. When you square the height of our silk ribbon, you turn those mathematical ripples into a solid, positive number that represents the chance of the particle manifesting at that spot. You might picture this like a cloud of fog settling into a valley at night. In the very center of the valley, the fog is thick, white, and opaque. As you move toward the hillsides, the fog becomes thinner, more transparent, until it finally vanishes at the ridge. The particle is like a shy ghost hidden somewhere in that fog. You are most likely to find the ghost where the fog is thickest. But there is a small, lingering chance you might find it out on the edges where the mist is thin. The wave function is the mathematical description of that fog. It tells us exactly how the thickness of the fog is distributed across the landscape of space. This leads us to the most famous equation in all of quantum science, the Schrodinger equation. While I will not show you the symbols, I want you to hear the rhythm of its meaning. The equation describes how this shimmering map changes over time. It tells us that the way the wave function ripples and flows is directly determined by the energy of the system. Imagine our silk ribbon again. If the ribbon is in a calm, empty room, it will spread out and flow smoothly. But if you place a heavy weight in the middle of the room representing a force like gravity or an electric field, the ribbon will bunch up and wrap itself around that weight. The Schrodinger equation is essentially the law of the ripple. It says that the rate at which the wave function changes as time passes is proportional to the total energy of the particle, its energy of motion plus its energy of position. If you know the energy of the environment, the equation allows you to calculate exactly how the wave of probability will evolve. It is a strange kind of determinism. We cannot predict exactly where the particle will be, but we can predict with absolute mathematical perfection how the probability of finding it will move and change. The maybe of the universe follows a very strict and orderly set of rules. Think about what this means for a single electron inside an atom. It is not a speck of dust orbiting a sun. It is a wave function that has settled into a stable, vibrating pattern like a note held perfectly on a violin string. The Schrodinger equation is the sheet of music that tells the electron how to vibrate. When the electron is unobserved, it exists as this spread out, beautiful pattern of here, there, and everywhere. It doesn't have a single location. It has a presence that is defined by the shape of its wave. This concept is the foundation of all modern chemistry and material science. When we design a new medicine or a faster computer chip, we are essentially using the Schrodinger equation to sculpt these wave functions. We are learning how to manipulate the shimmering maps of electrons so that they bond together in just the right way. We are not moving solid bits of matter. We are orchestrating waves of probability. As you let the image of this undulating, translucent map fill your mind, you might start to feel the profound implications of this spread-out reality. If the wave function says a particle is 30% likely to be in one spot and 70% likely to be in another, and we haven't looked at it yet, what is the particle actually doing? Is it just waiting in the shadows, or is it truly existing in both places at once? This brings us to one of the most mind-bending corners of our journey. If the map shows many possibilities, then the particle itself must inhabit all of them simultaneously. Before we rest here, let me whisper where we're headed next, not to rush, but to plant a seed. We have seen how the wave function describes a sea of possibilities. Now, we must ask what happens when those possibilities overlap. We move from the map itself to the strange state of being that the map describes. Let's set that idea of the wave function down now, fully formed, and let our attention drift toward the idea of both and, the mysterious and quiet world of superposition. Superposition, the art of being in many states at once. Before we rest here, let me whisper where we're headed next, not to rush, but to plant a seed. We have seen how the wave function describes a sea of possibilities. Now, we must ask what happens when those possibilities overlap. We move from the map itself to the strange state of being that the map describes. Let's set that idea of the wave function down now, fully formed, and let our attention drift toward the idea of both and, the mysterious and quiet world of superposition. Imagine for a moment that you are holding a single silver coin in the palm of your hand. It has two distinct faces, heads and tails. In our everyday world, the rules are very simple and very rigid. If you place that coin on a table, it is either heads up or tails up. It cannot be both. Even if you flip it into the air, we believe that at any given microsecond of its flight, it has a definite orientation, even if our eyes are too slow to see it. This is the world of either or. It is the binary logic that governs our lives, our computers, and our common sense. But as we sink deeper into the quantum layers of reality, this logic begins to soften and melt away, replaced by the beautiful and bewildering principle of superposition. To understand superposition, let us go back to that coin. Imagine you set it on its edge and give it a sharp, elegant flick so that it begins to spin rapidly on the tabletop. As it spins, the individual faces of heads and tails vanish. What you see instead is a shimmering, metallic blur, a silver sphere that seems to contain both possibilities at once. In this moment of spinning, the coin is in a state that is neither purely heads nor purely tails. If you were to describe it, you would have to say it is a combination of both. In the quantum world, particles like electrons and photons exist in this spinning state naturally. They don't just look like a blur, they fundamentally are the blur. This is what we mean by superposition. It is the ability of a quantum system to exist in multiple different states at the same time, as long as it is left alone and unobserved. It is as if the universe, when it isn't being watched, refuses to make up its mind. A particle isn't here or there. It is a little bit of here and a little bit of there, added together. We describe this mathematically as a linear combination of states. Imagine two musical notes being played at the exact same time on a piano. You don't hear one note and then the other. You hear a chord, a new singular sound that contains the essence of both individual notes. A quantum particle in superposition is a chord of existence. Now, you might ask, if everything is made of these particles, why don't I see the world as a shimmering blur of possibilities? This brings us to the most famous thought experiment in all of science, devised by Erwin Schrodinger to highlight just how strange this reality is. He asked us to imagine a cat placed inside a sturdy steel box. Along with the cat, there is a small device, a tiny sliver of radioactive material, a Geiger counter to detect radiation, and a glass vial filled with a deadly, poisonous gas. The experiment is set up so that there is a 50% chance that a single atom in the radioactive material will decay within 1 hour. If it decays, the Geiger counter will detect it, trigger a hammer, break the vial, and the cat will perish. If the atom does not decay, the cat remains perfectly safe. Because the decay of an atom is a quantum event, the atom exists in a superposition of decayed and not decayed as long as the box is closed. And because the cat's fate is tied to that atom, the logic of quantum mechanics suggests that the cat, too, must exist in a superposition. Inside that closed box, the cat is mathematically and physically both alive and dead at the same time. Schrodinger didn't propose this because he thought cats could actually be half-dead ghosts. He did it to show the tension between the quantum world and our own. He wanted to point out that there must be a moment where the blur of the spinning coin stops and the universe chooses a side. This moment is what we call the collapse of the wave function. The instant you open the box to look at the cat, or the instant you slap your hand down on the spinning coin, the superposition vanishes. The chord of many notes snaps into a single, solitary tone. The act of measurement, the simple act of an observer interacting with the system, forces the universe to settle on a single reality. Think about the profound stillness of that idea. In the dark, unobserved corners of the universe, reality is a lush, overflowing garden of maybes. Every possible path is being taken. Every possible outcome is happening at once. It is only when we turn our gaze toward it that the garden prunes itself down to a single, solid path. This suggests that we are not just passive spectators in the universe. We are the ones who, by the very act of living and observing, crystallize the mist of quantum possibility into the solid world we touch. This isn't just a philosophical dream. It is the engine behind the next great leap in technology, quantum computing. A classical computer uses bits, which are like light switches that are either on or off, 0 or 1. But a quantum computer uses qubits. Because of superposition, a qubit can be both 0 and 1 at the same time. Imagine you are trying to find the exit of a vast, complex maze. A classical mouse would have to try one path, hit a dead end, go back, and try another, one by one, until it found the way out. But a quantum mouse in a state of superposition could flow through the maze like a mist, exploring every single path simultaneously. It would find the exit almost instantly because it doesn't have to choose a path. It takes them all. As you let the image of this quantum mist fill your mind, you might begin to feel a sense of weightlessness. We are used to things being solid, fixed, and certain. But at the heart of matter, there is a freedom, a refusal to be tied down to a single state until the very last moment. This both-and nature of reality is the secret language of the stars and the atoms alike. But if a particle can be in many places at once, and if it is more like a spread-out wave than a solid grain of sand, then a new and even more impossible possibility arises. If the blur of an electron can exist on both sides of a barrier, can it somehow pass through things that should be solid? Can it defy the walls of the world? This leads us naturally to ask, what happens when the wave of possibility meets a mountain it cannot climb. That's what we'll gently explore next, as we look at the miraculous and quiet phenomenon of quantum tunneling. Quantum tunneling, the impossible journey through barriers. But if a particle can be in many places at once, and if it is more like a spread-out wave than a solid grain of sand, then a new and even more impossible possibility arises. If the blur of an electron can exist on both sides of a barrier, can it somehow pass through things that should be solid? Can it defy the walls of the world? This leads us naturally to ask, what happens when the wave of possibility meets a mountain it cannot climb? That's what we'll gently explore next, as we look at the miraculous and quiet phenomenon of quantum tunneling. In the world you and I inhabit every day, the world of sturdy tables, brick walls, and heavy doors, the rules of movement are very strict. Imagine you are standing at the bottom of a steep, grassy hill. At the very top of that hill is a goal you want to reach. To get there, you must have enough energy in your muscles to climb every single inch of that slope. If you only have enough strength to get halfway up, you will eventually stall, slide back down, and end up exactly where you started. You cannot simply wish yourself to the other side. In the language of physics, this is a potential energy barrier. To overcome it, you must possess an amount of energy equal to or greater than the height of the hill. Without that energy, the barrier is absolute. It is a no that the universe does not negotiate. But as we have learned, the quantum world does not speak in absolutes. It speaks in the language of the wave function. Let us return to our mental laboratory and imagine an electron moving toward a barrier. This barrier might be a thin layer of insulating material, or perhaps an invisible wall of electric force that is trying to push the electron away. In classical physics, if the electron doesn't have enough push, enough kinetic energy to overcome that wall of force, it will bounce back every single time. Like a tennis ball hitting a concrete slab, it is trapped on one side, destined to remain there forever. However, remember that our electron is not a solid ball. It is a shimmering cloud of probability. When this cloud reaches the barrier, something strange happens. The wave function, that mathematical map of where the electron might be, does not just stop dead at the surface of the wall. Instead, the math tells us that the wave bleeds into the barrier. It begins to fade, its height dropping off sharply and smoothly like the dying echo of a bell. But it does not instantly drop to zero. If the barrier is thin enough, if the wall is narrow enough, that fading wave can actually reach all the way through and emerge out the other side. Picture this in your mind as a ghostly mist. Imagine a thick stone wall. If you spray water at the wall, it splashes back. But if you blow a thick, heavy fog toward that wall, while most of the fog is blocked, a tiny, faint wisp of mist might find its way through the microscopic pores and appear as a ghostly ribbon on the far side. In quantum mechanics, that tiny wisp of wave function on the other side of the barrier represents a real, measurable probability. It means there is a small but definite chance that the electron, which didn't have the energy to climb the wall, will simply manifest on the other side as if it had tunneled through the solid rock without ever leaving a hole behind. This is quantum tunneling. It is the universe's way of saying that impossible is just a matter of probability. It is as if you threw a ball against a wall 1,000 times, and 999 times it bounced back, but on the 1,000th time, it simply vanished from your hand and reappeared in the garden on the other side. This isn't a trick of the light or a failure of our equipment. It is a fundamental consequence of the fact that matter is made of waves. Because the wave function is spread out in space, a tiny part of the electron's existence can exist beyond the barrier, even when the majority of it is blocked. Now, you might think this sounds like a rare laboratory curiosity, but the truth is far more profound. Without quantum tunneling, you and I would not be here to discuss it, because the sun itself would not shine. Imagine the core of the sun, a place of unimaginable heat and pressure. Deep inside, hydrogen atoms are trying to fuse together to create helium, a process that releases the vast amounts of energy that light our sky. But there is a problem. Hydrogen nuclei are all positively charged, and like magnets with the same poles, they repel each other with incredible force. They push away from each other so strongly that, even at the heart of the sun, they don't have enough classical energy to touch. By the rules of classical physics, the sun should be dark. It shouldn't have enough heat to force those atoms together. But because of quantum tunneling, the hydrogen nuclei don't need to climb the hill of repulsion. Every once in a while, two nuclei get close enough that their wave functions overlap, and they simply tunnel through the barrier of force to touch and fuse. It is a slow, rare event for any two specific atoms, but because there are so many trillions of them in the sun, it happens enough to keep the star burning for billions of years. Your very life is powered by atoms that are breaking the rules and tunneling through the impossible. We have even learned to harness this ghostly behavior in our own technology. Imagine a device called a scanning tunneling microscope. It uses a needle so incredibly sharp that the tip is made of a single atom. We hover this needle just a hair's breadth above a surface, so close that they aren't touching, but close enough that electrons can tunnel across the empty gap between the needle and the surface. By measuring this tiny, ghostly current of tunneling electrons, we can map out the individual atoms on a surface, seeing them not with light, but with the mist of their own wave functions. As you lie there, let the idea of the permeable world settle into your mind. The walls around you, the floor beneath you, even the barriers in your own life, at the most fundamental level, nothing is truly solid. Everything has a tail of probability that extends into the unknown. The universe is not a series of locked rooms, but a collection of spaces where the doors are always slightly, infinitesimally ajar. But if particles can tunnel through barriers and exist as spread-out clouds, we are led to an even deeper mystery. If an electron can be in two places at once, can it be connected to another electron in a way that transcends space itself? If the wave function of one particle can bleed into the world, can it become permanently woven together with the wave function of another? This brings us to a connection so deep that even Einstein found it unsettling. We move now from the impossible journey through walls to the invisible thread that binds the universe together. So what does this actually mean for how two separate things can act as one? That's what we'll gently explore next, as we drift toward the haunting and beautiful reality of quantum entanglement. Quantum entanglement, the invisible thread of connection. So what does this actually mean for how two separate things can act as one? That's what we'll gently explore next, as we drift toward the haunting and beautiful reality of quantum entanglement. We have seen how a single particle can be a spread-out wave, defying walls and existing in a shimmer of both and. But now, I want you to imagine that the blur of one particle becomes forever woven into the blur of another. This is perhaps the most profound mystery in all of physics, a phenomenon that suggests that at a very deep, fundamental level, The universe is not a collection of separate pieces, but a single, interconnected tapestry. Imagine you have two tiny, magical spheres. In the world of our everyday experience, if you take one sphere and place it in your pocket, and you give the other sphere to a friend who travels to the far side of the moon, those two spheres are entirely independent. Whatever you do to the sphere in your pocket, whether you paint it red, spin it clockwise, or drop it on the floor, has absolutely no effect on the sphere resting on the moon. They are separated by hundreds of thousands of miles of cold, empty vacuum. To send a message from your sphere to the other, you would have to beam a signal at the speed of light, and it would take more than a second for that information to arrive. This is what we call locality. It is the common sense idea that things can only be influenced by their immediate surroundings. But in the quantum world, particles can become entangled. This happens when two particles interact so closely or are born from the same event that their wave functions merge into one. They no longer have individual identities. They don't have their own maps of probability anymore. Instead, they share a single, unified map. And here is the spooky part that even Albert Einstein found impossible to accept. Once they are entangled, they remain a single system, no matter how far apart they are moved. Let us return to our mental coins to picture this connection. Imagine you and your friend each have one of these entangled quantum coins. You stay here on Earth, and your friend travels to the most distant star in the galaxy. As long as you haven't looked at your coins, they are both in a state of superposition, spinning in that shimmering blur of both heads and tails. But the moment you reach out and slap your hand down on your coin to see what it is, the blur collapses. Let's say your coin comes up heads. In that very same instant, not a second later, not a billionth of a second later, but perfectly simultaneously, your friend's coin on the far side of the galaxy stops spinning and shows tails. There is no signal sent between them. No invisible radio wave travels across the light years to tell the second coin what to do. The two particles behave as if they are right next to each other, even when they are separated by the entire width of the universe. It is as if space itself, the vast, empty distance we see between stars, does not exist for them. This is what we call non-locality. It suggests that the separateness we perceive in the world is, in some sense, an illusion. At the bottom of reality, everything that has ever interacted remains part of a grand, invisible web. Einstein was deeply troubled by this. He called it spooky action at a distance. He believed that there must be some hidden information inside the particles, like a secret instruction manual they both carried from the moment they were born. He thought that if the coins always came up in opposite ways, it was simply because they had been programmed that way at the start. But decades later, a physicist named John Bell proved through a brilliant and elegant, logical argument that Einstein was wrong. There is no hidden programming. The particles truly don't decide what state they are in until the moment one of them is measured. The connection is real, it is instantaneous, and it defies our understanding of time and space. To understand why this happens, we can look at a property of particles called spin. In the quantum world, certain pairs of particles are created with a total spin of 0. Because of a fundamental law called the conservation of angular momentum, the universe demands that the total spin stays at 0. This means that if one particle is found to be spinning up, its partner must be spinning down to balance the cosmic scales. The mystery isn't that they are opposites. The mystery is that they don't choose which one is up and which one is down until you look at one of them. And once that choice is made, the information is shared across the universe instantly. Think about the implications of this as you lie here in the stillness. Entanglement tells us that the universe has a memory. It tells us that the history of every interaction is preserved in these invisible threads of connection. Scientists are already using this spookiness to develop quantum teleportation, not of solid objects, but of information, and to create unbreakable codes for communication. If you try to eavesdrop on an entangled message, the very act of your looking collapses the entanglement, leaving a clear sign that someone has interfered. But beyond the technology, there is a poetic truth to entanglement. It reminds us that we are part of a whole. Every atom in your body was once forged in the heart of a dying star, interacting with countless other atoms in that fiery furnace. If those interactions created entanglements, then in a very real physical sense, you are still connected to the distant reaches of the cosmos. You are not a lonely island in a dark sea. You are a note in a vast, echoing chord that spans all of existence. This profound unity, this spooky connection that ignores the barriers of space, is one of the pillars of the quantum world. It shows us that reality is far more fluid than it appears. Yet, even in a world where things can be in two places at once and connected across galaxies, there are still rules. There is still a logic that prevents the universe from collapsing into a chaotic heap. Even these spooky particles must obey a strict code of conduct that gives our world its shape and solidity. As we let the image of these invisible threads of connection drift in our minds, we begin to realize that this unity is what allows for structure. If particles can be so deeply linked, then there must also be rules about how they can sit together and how they must stay apart. This brings us to the principle that ensures you don't fall through your chair and that the ground beneath you stays firm. We move now from the invisible threads of entanglement to the no occupancy rule of the atom. So what does this actually mean for how two separate things can act as one? That's what we'll gently explore next, as we look at the Pauli exclusion principle and the reason the world has shape. The Pauli exclusion principle. Why the world has shape. So what does this actually mean for how two separate things can act as one? That's what we'll gently explore next, as we look at the Pauli exclusion principle and the reason the world has shape. A moment ago, we ended with the haunting idea of quantum entanglement, the invisible threads that connect particles across the vastness of space. But if entanglement is the thread that weaves the universe together, the principle we are about to discuss is the structure that prevents it from all collapsing into a single, shapeless point. It is the rule of boundaries, the law of no occupancy, and it is the reason that you, the chair you are sitting in, and the very ground beneath you feel solid and real. Imagine for a moment a universe without any rules of exclusion. If particles could simply occupy the same space without limit, there would be no reason for atoms to have size. Electrons would all simply fall into the very center of the atom, crowding together in a tiny dense heap around the nucleus. Matter would have no volume. Solids would not exist. Everything would be a ghostly, overlapping soup of energy. But the universe is not a soup. It is a structured masterpiece. This stability is thanks to a young Austrian physicist named Wolfgang Pauli, who in 1925 discovered a fundamental law that governs the behavior of a specific class of particles called fermions. Fermions are the building blocks of matter. They include the electrons, protons, and neutrons that make up your body. And Pauli's principle is wonderfully simple to state, yet profound in its consequences. No two fermions can ever occupy the exact same quantum state at the exact same time. To understand what this quantum state means, let us return to our favorite analogy of the cosmic address or zip code. Remember the four quantum numbers we discussed: the energy level, the shape of the orbital, the orientation in space, and the spin. Together, these four numbers form a unique identity for an electron. Pauli's rule says that in any given atom, no two electrons can share the same four numbers. They cannot have the same address. To picture this, imagine a grand, ancient hotel, the Hotel of the Atom. This hotel is built with many floors, representing the energy levels. On each floor, there are different types of rooms: simple circular rooms, elegant, double-lobed suites, and complex, multi-room apartments. These are the orbitals. Now, the rule of this hotel is very strict. Each bed in each room can only hold one guest. In our quantum hotel, every bed is a specific combination of energy, shape, and orientation. But there is a small loophole. Every bed is actually a bunk bed, with a top and a bottom. This represents the spin of the electron. One electron can sleep in the top bunk spinning up, and another can sleep in the bottom bunk spinning down. But that is the limit. Once those two bunks are filled, that room is officially and legally at capacity. If a third electron arrives at the hotel, it cannot squeeze into that room, no matter how much it might want to. It is forced to move to a different room, or perhaps even to a whole new floor with a higher energy level. This no vacancy rule is the Pauli exclusion principle in action. Because electrons are forced to move into higher and higher floors and more distant rooms to find a place to stay, the atom begins to take up space. It expands. It develops layers, like the skin of an onion. This layering is what gives the world its incredible variety. As we move through the periodic table, each new element adds one more electron to the hotel. Hydrogen has one guest in the very first room. Helium fills that first room with its second guest. But when we reach lithium, the third element, the first room is full. The third electron must move up to the second floor. As we continue adding guests, the hotel of the atom grows more complex, with more floors and more elaborate room designs. This is why chemistry exists. The way atoms interact with each other depends entirely on how many vacant beds are left on their top floor. If the top floor is full, the atom is content and stays to itself, like the noble gases. If the top floor has empty beds, the atom will go looking for neighbors to share with. But there is an even more fundamental consequence to this rule. Have you ever wondered why you don't fall through the floor? Or why, when you press your hands together, they don't simply pass through one another like mist? You might think it's because the atoms are touching, like solid marbles. But remember, atoms are mostly empty space, vast clouds of probability, with a tiny nucleus at the center. The reason you feel solidity is actually a beautiful display of quantum resistance. When the electrons in your hand get too close to the electrons in a table, they try to occupy the same space. But Pauli's principle says they cannot. To avoid sharing the same state, those electrons would have to jump to much higher energy levels, which requires a massive amount of force. This pushback is what we call exchange interaction or degeneracy pressure. It is a silent, invisible force that says no to the overlapping of matter. When you sit in a chair, you are actually levitating on a cushion of quantum exclusion. You are being held up by the fact that the electrons in your body refuse to occupy the same quantum rooms as the electrons in the chair. It is the most powerful keep out sign in the universe. In the world of the very large, this principle even holds up the stars. When a massive star dies and collapses under its own gravity, it becomes so dense that the atoms are crushed together. But the electrons within those atoms scream out a final no. They refuse to be crowded any further, creating what we call electron degeneracy pressure. This pressure is so strong that it can stop the collapse of an entire star, leaving behind a white dwarf, a star the size of the Earth, but with the mass of the Sunday. It is a diamond-hard ember, held up by nothing but the Pauli exclusion principle. As you breathe in and out, let the sense of this sturdy, well-ordered universe settle over you. You are held together by a beautiful logic that demands individuality. No two parts of you are trying to be the same. Every electron has its own place, its own rhythm, and its own address. This rule of exclusion is what brings the maybe of the wave function into the is of the physical world. It transforms the shimmering clouds of probability into the solid, dependable objects we love. But even with these rigid rules in place, we are still left with a lingering question. If the math is so perfect and the rules are so strict, what does it all actually mean? How do we reconcile this world of maybes and no occupancy rules with the reality we see when we open our eyes? That's what we'll gently explore next. We have seen the rules that give the world shape. Now, we must look at the different stories we tell ourselves to make sense of them. We move from the laws of matter to the interpretations of the mind, as we consider the different ways we might view the quantum mirror. Seeking meaning in the math. The Copenhagen versus many worlds interpretations. We have seen the rules that give the world shape. Now, we must look at the different stories we tell ourselves to make sense of them. We move from the laws of matter to the interpretations of the mind, as we consider the different ways we might view the quantum mirror. This brings us to a peculiar crossroads in our journey. Up until now, we have discussed the how of quantum mechanics, the way waves ripple, the way particles tunnel, and the way electrons occupy their atomic hotels. The mathematics that describes these events is the most successful in human history. It has never been proven wrong. But there is a haunting gap between the math on the page and the world we see when we open our eyes. This gap is what physicists call the measurement problem. And to solve it, we must step out of the laboratory and into the realm of philosophy. Imagine for a moment that you are a master musician. You have a sheet of music that perfectly describes a beautiful, complex symphony. The notes are all there, the rhythm is precise, and the harmony is flawless. This sheet of music is like the Schrodinger equation, the mathematical wave function that tracks all the possibilities of a particle. According to the music, the symphony should go on forever, with every instrument playing its part in a grand, overlapping wave of sound. But in our actual experience of the world, we don't hear the whole symphony at once. We only ever hear a single solitary note at any given moment. Why does the music of all possibilities suddenly snap into the sound of just one? This question led to the birth of the Copenhagen interpretation, pioneered in the 1920s by Niels Bohr and Werner Heisenberg. It remains the standard way that quantum mechanics is taught in colleges around the world. The Copenhagen view suggests that we should stop asking what the universe is doing when we aren't looking. According to Bohr, there is no real world of particles underneath the wave function. There is only a mathematical description of what we might find if we look. In this view, the act of measurement is a violent and transformative event. Picture a spinning coin on a table once more. While it is spinning, it is a blur of heads and tails, a superposition. The Copenhagen interpretation says that the moment you look at the coin, you force it to collapse. The wave function, which was spread out and flowing, suddenly shrivels up into a single point of reality. One possibility becomes real, and all the others simply vanish, as if they never existed. To the Copenhagen school, the observer is the key. It is the interaction between the large-scale world of the scientist and the tiny-scale world of the atom that creates reality. Until that interaction happens, the universe remains a ghostscape of maybe. It is a humble and cautious view, suggesting that there are veils over nature that we may never be able to lift. But many scientists found this collapse to be deeply unsatisfying. They asked, if the Schrodinger equation is a perfect description of the universe, why would it just stop working when a human looks at it? This discomfort led a young physicist named Hugh Everett III to propose a radical alternative in the late 1950s, the many worlds interpretation. Everett suggested that the wave function never collapses. It never shrivels up. Instead, it just keeps growing and flowing, encompassing everything it touches, including the observer. To understand many worlds, imagine you are standing in front of a mirror that is also a doorway. In the Copenhagen view, when you flip a quantum coin, the mirror cracks, and only one you survives to see the result. But in the many worlds view, the mirror doesn't crack, it branches. Every time a quantum event has more than one possible outcome, the entire universe splits into different versions of itself. If you flip a coin that is in a superposition of heads and tails, the universe branches into two. One where you see heads and one where you see tails. Picture a vast, ancient oak tree in the moonlight. Each branch represents a path the universe has taken. As you move from the trunk to the smaller branches, you are following a specific history. But the other branches are still there, existing just as vibrantly as the one you are standing on. In this interpretation, every maybe becomes an is, somewhere in the multiverse. Every choice you didn't make, every path you didn't take, and every possible version of your life is playing out in a different branch of an unfathomably large wave function. There is no collapse, only a continuous, infinite blooming of reality. While this sounds like science fiction, it is actually a more literal reading of the mathematics than the Copenhagen view. It removes the need for a mysterious observer to trigger a collapse. Instead, it suggests that we are simply small parts of a giant, entangled system. The reason you only see one outcome is because you too have branched. You are part of the heads universe, or the tails universe, and you can no longer see the other branches because you are no longer entangled with them. These two interpretations, Copenhagen and many worlds, are like two different lenses through which we can view the same shimmering quantum mirror. One tells us that reality is created by the act of looking. The other tells us that everything that can happen does happen, and we are just along for the ride on one particular branch. They both use the same math, and they both predict the same results in our experiments. The difference is entirely in the story we choose to believe. This connective thread between math and meaning shows us that science is not just a collection of cold facts. It is a human endeavor, a way of trying to find our place in a universe that is far stranger than our ancestors ever dreamed. Whether the wave function collapses into a single moment of grace or branches into an infinite garden of lives, the result is the same. You are here, in this moment, a part of a reality that is fundamentally interconnected and full of potential. As you let these two stories drift through your mind, the shriveling wave and the branching tree, you might feel a sense of profound freedom. The quantum world tells us that the future is not a single, locked track, but a sea of possibilities. It tells us that the universe is not a finished book, but a story that is being written with every interaction, every measurement, and every breath. So what does this actually mean for the world you see when you wake? How do these maybes and branchings support the solid reality of your daily life? That's what we'll gently explore as we reach the final destination of our journey. We move now from the interpretations of the mind to the grand, foundational legacy of the quantum world. Before we rest here, let me whisper where we're headed next. Not to rush, but to plant a seed of the final reflection on how this foundation supports every breath you take. Let's set these stories down now, letting them settle beside you like old friends, and let our attention drift toward the quiet, enduring truth of the quantum foundation. The quantum foundation of reality, a legacy of wonder. So what does this actually mean for the world you see when you wake? How do these maybes and branchings support the solid reality of your daily life? That's what we'll gently explore as we reach the final destination of our journey. We move now from the interpretations of the mind to the grand, foundational legacy of the quantum world. Before we rest here, let me whisper where we're headed, not to rush, but to plant a seed of the final reflection on how this foundation supports every breath you take. Let's set these stories down now, letting them settle beside you like old friends, and let our attention drift toward the quiet, enduring truth of the quantum foundation. We began our journey at the gateway of the subatomic realm, leaving behind the comfortable, predictable clockwork of Isaac Newton. We watched as the smooth ramps of classical physics transformed into the jagged, beautiful staircases of Max Planck's quanta. We saw light reveal its dual nature, acting as a gentle wave one moment and a hail of energetic photons the next. We witnessed the strange dance of electrons as they refused to be pinned down, existing instead as shimmering clouds of probability, tunneling through impossible barriers and remaining connected across the silent reaches of space through the mystery of entanglement. It is easy, in the quiet of the night, to feel as though these ideas are just ghost stories, fascinating tales told by physicists to explain the invisible. But as you lie there, I want you to realize that quantum mechanics is the most real thing you have ever encountered. It is not just a theory. It is the very fabric of the world you touch, smell, and see. If the rules of the quantum world were to suddenly vanish, the universe would instantly lose its shape. Without the Pauli exclusion principle, your body would collapse into a point 1,000,000,000 times smaller than a grain of sand. Without quantum tunneling, the sun would go dark, and the earth would freeze in the silent blackness of space. Consider the technology that surrounds you in your waking life. Every time you look at a digital screen, you are seeing the legacy of the quantum. The transistors that live inside your phone and computer, the tiny switches that allow information to flow work because we learned how to manipulate the way electrons move through layers of silicon using the laws of quantum mechanics. When you go to a hospital and see an MRI machine, you are looking at a device that uses the spin of the protons in your own body, that internal magnetic orientation we discussed to create a map of your internal health. Even the global positioning system that guides you through the streets depends on atomic clocks that measure time using the precise quantum vibrations of atoms. We have moved from being victims of nature's mysteries to being architects of its most fundamental laws. We have learned to speak the language of the atom, and in doing so, we have built a civilization that would look like magic to our ancestors. But perhaps the greatest legacy of quantum mechanics is not the machines we have built, but the way it has changed our understanding of ourselves. It has taught us that the universe is not a collection of separate, lonely objects bumping into each other like billiard balls. Instead, it is a vast, interconnected field of energy and potential. Think of the atoms in your own body. Most of them were forged billions of years ago in the hearts of distant stars. Those stars exploded, scattering their elements across the galaxy, eventually coming together to form the Earth and, eventually, you. Because of quantum entanglement, the particles that make you up carry with them the silent history of every interaction they have ever had. You are, in a very physical sense, a part of everything you see. There is no hard line where you end and the universe begins. You are a localized ripple in a cosmic ocean of probability. As we reach this place of rest, let the weight of these ideas become light. You don't need to hold on to the math or the names of the scientists. What matters is the quiet sense of wonder that remains. You are living in a universe that is far more vibrant, far more mysterious, and far more connected than we ever dared to dream. It is a world where the act of looking is a creative act, and where the fuzziness of reality is what gives it its strength and its beauty. Imagine the universe now as a great, silent symphony. Each section of our journey, from the waves of light to the exclusion of matter, has been a different instrument joining the arrangement. Together, they create the harmony that allows stars to burn, plants to grow, and you to dream. The maybe of the quantum world is not a weakness. It is a profound kind of freedom. It means that the future is not a single, unchangeable track. It is a garden of branching paths, a sea of possibilities that is waiting for you to wake up and walk through it. But for now, the walking is done. The journey is complete. You have let these truths wash over you like a gentle tide, and they have settled deep within the layers of your mind. You have navigated the sea of the wave function and found your way back to the shore of your own quiet room. The jittery uncertainty of Heisenberg has softened into a peaceful stillness. The both and of superposition has allowed you to be both a student of the stars and a sleeper in the dark. And so we come to the end of our time with quantum mechanics fundamentals. Not an ending, really, but a place to rest. You've let these ideas settle beside you as you slept, and they'll be here whenever you return. The universe will continue its silent quantum dance while you dream, weaving its invisible threads and maintaining its beautiful, exclusion-built structures. You can trust in the solidity of the floor and the warmth of your breath, knowing that they are supported by a foundation of infinite wonder. Until then, sleep well and carry nothing but the quiet sense that you understand a little more than you did before.